All right, let's take a look at our test questions. I'm going to go ahead and share my screen here. Okay, so we'll look at question number 1 and question number 2 first. Both of those are using the same instructions. It says, assume that the weight loss for the first month of a diet program varies between 6 pounds and 12 pounds and is evenly spread over a range of possibilities, so there is a uniform distribution. So that tells me that I need to write X is uniformly distributed from 6 to 12. And when we did this, we went ahead sometimes and we would label the first number as our A value and the second number as our B value. So if we're going to find the probabilities here, we need to draw a rectangle. Our rectangle is going to start with the A value 6 and our B value 12, and then we're going to determine what they're asking for each particular problem. So they want the probability that the range of pounds lost is between 9 and 12 pounds. So if this is 6 and this is 12, the 9 is going to be down the middle here. And if we want between 9 and 12 pounds, we're going to go all the way to the end because 12 is our end number here. So we're looking for the area of this shaded rectangle. So we need to also go ahead and find our height on that rectangle, which we always did by using f of x is 1 over b minus a. And again, our b in this case is the 12, our a is 6, so our height is going to be 1/6. So height on this full rectangle is 1 over 6. And so we're going to multiply the 1/6 times the base between 9 and 12. So we can write that as the probability that x is greater than 12. You could do between 9 and 12, but in this case, because we're going all the way to the end, x is greater than 12 works for our symbol. And we're going to put 12 minus 9 for the base. And we need to multiply the base times the height, so we're going to multiply by the 1/6. So 12 minus 9 is going to give us 3. And 3 times 1/6 is going to give us 3/6, which I know that one as a decimal already is going to be 0.5. So we're actually looking for answer choice D for number 1. Okay, so number 2, we're going to use the same starting rectangle where we start at 6 and end at 12. And it'll have the same height of 1/6. But now it says, what's the probability that the weight lost is more than 7 pounds? So more than 7 pounds is going to be more of this rectangle shaded in. But we're going to do exactly the same thing in terms of base times height. So in this case, I'm going to do the base is the 12 minus the 7. And how I can write the probability is that x is greater than 7. And actually, I just noticed looking at this one, I don't know, I said probability x is greater than 12. Probability x is greater than 9. And it went up to 12. I think I was talking too fast. So let me change the last one's notation. Probability x is greater than 9. There we go. So this one, probability x is greater than 7, is going to be the 12 minus the 7 for the base. And the height remains the same, 1/6. So 12 minus 7 is going to be 5, and 5 times 1/6 is 5/6. If we put that into our calculator, we get about 0.83, which is going to be answer choice D. Okay. So those were our uniform distribution problems for the test. Number 3 says, find the area of the shaded region. The graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So the mean I'm going to use is 100. The standard deviation I'm going to use is 15. And so the value that is marked off on this graph in the shaded region is 110. So this is going to be a normal CDF problem. And I can tell that it's shaded from negative infinity up to the 110 value. So on this side, we got negative infinity. On this side, we got positive infinity. And in terms of shading, we always come from the left. So from the left, the first thing that shades is negative infinity. We put that into our calculator as negative 10 to the 99th power. And then we go all the way up to the end of our shaded region, which is 110. And then the last two values that I put in are always the mean and the standard deviation. So I'm going to put in the 100 and I'm going to put in the 15. And if I enter that into the normal CDF function on the calculator, we end up with 0.7475, which is going to be answer choice B. Number 4 says, find the indicated IQ score. The graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So same two values as the last problem. But now it says the shaded area under the curve is 0.10. So they're telling us that we have 10% of the data in this tail over here. And so they're asking us to figure out what IQ score would represent the top 10% of all of the data here. So that would be the same thing as going to figure out your 90th percentile if the top 10% is shaded in. So if we want the 90th percentile, we're going to use the inverse norm. And we're not going to use the 10th percentile because that would mean that I was over here and it was this tail. I want inverse norm for the 90th percentile. So I'm going to put 0.90 in there. And then we always put in the mean and the standard deviation. So we're going to put in 100 and we're going to put in 15. And so if we plug those into the inverse norm function on the calculator, what pops out is 119.2 approximately. So that's going to give us answer choice B for number 4. Human body temperatures are normally distributed with a mean of 98.2 degrees and a standard deviation of 0.62 degrees. So we could write our normal distribution information here. Mean is 98.2. I'll put in the 2 zeros just because it's got both there. And then standard deviation 0.62. And it says find the temperature that separates the top 7% from the bottom 93rd percent. So if we're going to find the top 7%, the value that separates it from the bottom 93%, that's going to be the 93rd percentile because we were looking up here for the value that separated the top 10% from the bottom 90%, and that was the 90th percentile. So these are very similar problems. So we're going to use inverse norm again. This time we're going to put in 0.93. And then the mean we're going to use is 98.20. And the standard deviation 0.62. So if you plug this into your calculator, about 99.1 degrees will pop out. So we're going to use answer choice D for this one. Assume that X has a normal distribution and find the indicated probability. Okay, so if X is normally distributed and they're telling us the mean is 60 and the standard deviation is 4, find the probability that X is less than 53. This would be one that I would do a little sketch for myself so that I know how to put it into my calculator properly. So we're going to put the 60 down the middle for the picture. And then they're asking, find the probability X is less than 53. So 53 would be over on this side then. And less than 53, we'd shade over to the left tail. So when we shade the left tail, that tells us when we go to do our normal CDF, that when we're coming from the left, the first number that we hit is negative infinity, and we use negative 10 to the 99th power for that. And as we keep going, the end of that shaded region is the 53. And the last two numbers we put in are from the distribution. We'll put in the 60 and the 4. So if you plug this into normal CDF on your calculator, you'll get 0.0401 approximately, which is going to be answer choice B. Number 7 is very similar. It's keeping same sort of format, but this time X is normally distributed with a mean of 15.2 and a standard deviation of 0.9. And so we're going to find the probability that X is greater than 16.1 by, again, drawing ourselves a little sketch so that we can see how to put it into the calculator. So down the middle, we're going to put the 15.2. And so finding the probability that X is greater than 16.1 means 16.1 is over on the right-hand side. And so we're going to shade the right tail. And if we shade the right tail, then when we go to put this into the normal CDF, then what we're going to start with is the very first number of the shaded region is the 16.1. And then the end of the shaded region would be positive infinity, and we'll use positive 10 to the 99th power for that. And then the last two numbers that we put into the calculator are going to be the mean, 15.2, and the standard deviation, 0.9. And so if you enter these numbers into the normal CDF, what will pop out is approximately 0.1587, which will be answer choice B again. Okay. Number 8. Very similar type of problem. It's telling us that X is normally distributed with a mean of 15.2 and a standard deviation of 0.9. And this time they're asking for the probability that X is between two numbers. And so when I go between two numbers, I don't usually draw myself a sketch. You can, but I didn't for this one. So we're going to do the normal CDF. And then we just go ahead and put in the lower number, 14.3. The higher number, 16.1. And then the two numbers from the distribution, the 15.2 and the 0.9. And so if you enter all those numbers into the normal CDF on your calculator, you'll end up with 0.6827 approximately, which will be answer choice C for us. Okay. Number 9. Just as find the indicated probability, so we're going to have to figure out what distribution we're talking about. The lengths of human pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. What is the probability that a pregnancy test lasts 300 days? So this doesn't have any sample in here or anything like that. So this is just another normal distribution problem. And it's normally distributed from 268 is our mean, and 15 is our standard deviation. So I'm going to go ahead and draw myself a sketch so that I can see where all that is in relation to the 300. So down the middle of the distribution, we put the 268. And that means that the 300 is off to the right-hand side. And since it says, what's the probability of pregnancy lasts at least 300 days, that means we want to shade above the 300, so we're going to shade in the right tail. So normal CDF. And we always come from the left-hand side. The first number that I hit is the 300 in that shaded region. And then we go all the way to the end of the shaded region. That's going to be infinity. So we use 10 to the positive 99th power for that one. And then the two numbers from our distribution. 268 goes in for the mean and 15 goes in for the standard deviation. And so if we enter that into normal CDF on our calculator, we get 0.0164 approximately, which is going to be answer choice C. So all those are a bunch of normal distribution problems. No central limit theorem yet. Number 10. For women aged 18 through 24, systolic blood pressures these are units for blood pressure, are normally distributed with a mean of 114.8 and a standard deviation of 13.1. If 23 women aged 18 through 24 are randomly selected, find the probability that their mean systolic blood pressure is between 119 and 122. So they're giving us a sample this time. And I'm worried because it's not 30 or greater that I would normally need for central limit theorem, except that it told us that it's normally distributed. So we're okay. So I can still use my central limit theorem. So X is normally distributed from 114.8 for the mean and 13.1 for the standard deviation. And then because of the fact that this is going to be a sample of 23, this would be if it was just the normal distribution, but if we're going to talk about the means here, I'm going to say that the sample mean is normally distributed with a mean of 114.8. We leave that one the same, but now we're going to put the standard error in here. So we're going to put the 13.1 divided by the square root of the sample size, which we said was 23. And so we need to put in the standard error into the calculator when we go to do the calculation for this one. And so we'll get that value in just a second. Because this is a between 119 and 122, I don't necessarily need to draw a picture for this because I already know what the lower number and the upper number need to be. We're still going to use the normal CDF. And we'll put the 119 first, the 122 second, and then we put the numbers from our central limit theorem's distribution for the sample means. So I'm going to put the 114.8, and then I'm going to figure out what's the 13.1 divided by the square root of 23. And so in my calculator, that comes out to be about 2.7315 if I round it to 4 decimals. And so putting these 4 values in for the normal CDF pops out 0.0579. And that's going to be our answer choice A. Okay, so Notice the difference between number 9 and number 10 was number 9, we just went ahead and used the regular normal distribution. But for 10, even though they said that it's normally distributed, then they told us it's a sample. And so we needed to know it was normally distributed because our sample size isn't big enough for us to just go off central limit theorem on its own. But now that we know that it's normally distributed, we're going to go ahead and take that standard deviation and divide it by the square root of 23. So that was us using the standard error. So this final exam here, we're going to assume is normally distributed with a mean of 73 and a standard deviation of 7.8. Again, we're talking about 24 students in a sample being randomly selected. Find the probability that the mean of their test scores is greater than 71. So we're going to go ahead and again do the X bar distribution for this one, which means that we're going to just go ahead and use the mean that they told us, which was 73. But we're going to use the standard error instead of the standard deviation. So I'm going to put the 7.8 on top, but we're going to divide it by the square root of 24 here. Okay. And so when we go to put the into our calculator, because it just says greater than 71, I probably want to sketch so that I know where is my starting place and ending place. And so the mean's going to be 73 down the middle. And finding the probability that greater than 71 means that we're going to be shading in more than half of the distribution then, because if it were from just 73 over, that would be 50%, but we've gone a little bit further than that to get to the 71. So I know my answer should be bigger than 50%, but not hugely different than 50%. So I'm really thinking it's probably going to be something like maybe the 60 or the 81 in there, but I don't know yet based on the numbers, just by looking at the picture. So we're going to take our normal CDF. And coming from the left-hand side, the first number that I hit in the shaded region is the 71. So that's going to go in first. And then I'm shading all the way to positive infinity. So we're going to do 10 to the 99th power for that. And then we're going to put our two numbers that are in the distribution here. So we're going to put down the 73. And then in my calculator, I'm going to figure out what's 7.8 divided by the square root of 24. That comes out to be 1.5922 approximately. And so putting those four numbers into the calculator for the normal CDF is going to give us 0.8955. So a little bit more than what the picture was looking like just based on how I drew it. It was answer choice A for this one. So both of those ones fell under central limit theorem because we were talking about a sample. So we had a sample of 23 people for this one, so we needed to divide by the square root of 23. And we had 24 students. And we're talking about means of test scores. Those are normally distributed. And we're going to divide by the square root of that sample size. So when we're doing central limit theorem problems, you're using the standard error instead of the standard deviation. All right, different types of problems down here. Find the critical value T sub C. So this is just the T critical value for C, which is a confidence interval of 0.99. And we're talking about a sample size of 10 in this case. So our confidence interval level, 0.99, our sample size of 10. When we want to find the T critical value, we use the inverse T function. Okay, and when we do the inverse T function, it wants the area, and then it wants degrees of freedom in there. So we need to go find an area and degrees of freedom. When we do the inverse T, and they're telling us that we have a confidence level of 99%, the picture that I'm going to draw to help me figure out the area is that if we're talking about a 99% confidence interval, I'm filling in almost the entire interval. So sorry, this is the 99% in the middle here. So from this point to this point is like our 99%, which means that we still have 1% left over that has to get divided between each of these two tails. And when we figure out the area, I only count this tail. And then what we do is we take the whole area from just the one tail and then the area for the confidence interval, but we don't include the last tail. So if there's 1% left over in both tails, that means there's 0.05%, or sorry, not 0.05, but 0.5%. I went a little too low there, 0.5% in just this one tail. So 99% and then 0.5%, that's going to be 99.5%, which if we write that as the area, we want to turn it back into its decimal. So that's going to be 0.995 for the area. So into the calculator, when we get to the area part for the inverse t, we're going to put 0.995. And then degrees of freedom is always n minus 1. So they told us that n is 10. So we're going to do 10 minus 1. We're going to use 9 for the degrees of freedom. So the inverse t function, we're going to enter 0.995 and 9. And so into our calculator, if we do that, the critical t value that we get is approximately 3.250, which will be answer choice B. So we have another chance to practice this for question 13. It's also asking us for the critical t value, but this time the confidence interval is a 95% confidence interval. So I'm going to draw another distribution, and this time we have 95% taken care of in the middle, which means there's still 5% between the two tails. I only want to take care of one of the tails, so if there's 5% total, there's 2.5% in just this tail over here. So I only want to include the one tail on this side, and then the confidence interval, we're going to exclude the second tail. So that would be 97.5%. But as an area, we'll write that in decimal form as 0.975. And then degrees of freedom, again, that's going to come from taking the n minus the 1. So we'll use 15 for the degrees of freedom. So in our calculator, we're going to do inverse t again. For the area, we'll enter 0.975. And for degrees of freedom, we'll enter 15. And if we put that into our calculator, we're going to get approximately 2.131, which is answer choice A. Find the value of E, or the margin of error, for the 95% confidence interval with a sample size of 10 and a sample standard deviation of 3.2. And so I wrote up on the board in class that this E is the same thing as our error bound for the mean, which some people had it written like that on their formula sheet. Totally fine. What we want for the error bound for the mean is the critical t value times the standard deviation for the sample divided by the square root of our sample size. So that was hopefully on your formula sheet. We need to go find our t critical value for a 95% confidence interval where we have a sample size of n. So we're going to do the inverse t. I don't need to draw another picture because we did a 95% confidence interval for the last one, and we knew that the area was 0.975, so we'll use that area again. But this time for our degrees of freedom, we're going to use 9 because our sample size is 10. So we're going to do 10 minus the 1, so we're going to plug in 9. So our T critical is going to be 2.262 approximately. So that's this part of the formula. And then for the sample standard deviation, we'll plug in the 3.2. And then for the sample size, we'll plug in our square root of the 10. So we have all the numbers that we need. 2.262 times 3.2 divided by the square root of 10. And if we plug that into our calculator, we get approximately 2.29, which was answer choice A. Right, number 15 is actually asking us to construct the confidence interval for the population mean using the T distribution. They told us we need a 99% confidence interval. We're going to use a sample mean of 22.4. Our sample standard deviation is 3.8, and our sample size is 19. When we want to do a confidence interval and they're not asking us for the error or the critical value, we can just go ahead and use the cheater method on this one. In this case, the fast way to do it is the T interval. T interval on our calculator then asks us for the X bar, which is the 22.4. Then it asks us for the sample standard deviation. We'll enter the 3.8. Then it asks us for the sample size. So we'll put in our N is 19. And then the last thing it asks for is the C level or the confidence level. And so we'll put in 0.99 for that. So into T interval, we enter those 4 values and it does all the work for us and it pops out 19.891 and 24.909. And then we need to look at which of those would match up here. So 19.89, if we round to 2 decimal places, will be there. And 24.91 would be the value here. So we're going to use answer choice B for that one. But the calculator took care of all that for us. We didn't have to do the complicated way. All right. In a random sample of 28 families, the average weekly food expense was $95.60 with a standard deviation of 22.50 or $22.50. Determine whether a normal distribution or a T distribution should be used and whether neither of these can be used to construct a confidence interval. Assume the distribution of weekly food expenses is normally shaped. So because this is normally shaped, but we're taking a sample of 28 families, this is going to be central limit theorem. And when we do central limit theorem, we use the T distribution for us over here. So we are going to use answer choice C for this one. So not a normal distribution. We use the normal distribution when we do the population proportion problems, but when we do the sample means, we go ahead and use our T distribution. All right, number 17, construct a 95% confidence interval for a population mean. Assume the population has a normal distribution. A random sample of 16 fluorescent light bulbs has a mean life of 645 hours and a standard deviation of 31 hours. So again, they're telling us, assume it's a normal distribution, but we're doing a sample. So it's okay that our sample is less than 30. We're only at 16 for this one, but that's A-okay. Again, they're not asking us to calculate the error separately or anything like that, so we can use the cheater method again with the T interval. And it'll do the work for us. So in the T interval, they want us to enter the sample mean of 645. The next thing they want us to enter is the sample standard deviation, which is 31. The next thing they ask for is the sample size, the N value, which is 16. And then it asks for what confidence level we want, and it wants a 95% confidence level for this one, so we'll put 0.95. And so if you enter those four values into the t interval, it'll do the work for you. And what will pop out is 628.48 and 661.52, which is going to be answer choice A. And we're just rounding to one decimal place for those ones. Number 18 says, a survey of 280 homeless persons showed that 63 were veterans. Construct a 90% confidence interval for the proportion of homeless persons who are veterans. Again, this one didn't ask for the error or anything like that, so we can do the cheater method for the confidence interval, but this one's going to be proportion, so we're not going to use the t interval, we're going to use the 1 proportion z interval. And what that one asks you for is the x value, the n value, and the confidence level. If you're not sure from these numbers which of those are the numbers in the problem, you might want to write out what the p hat formula is. The p hat is the x divided by the n, and that might help trigger what should go in the top and what should go in the bottom. So total number of people asked would be our n value. So the 280 is going to be the n, and then the 63 is going to be the x value. So that'll help with the calculator part. So when the calculator asks you for the x value, you're going to put in 63. When they ask you for the n value, you're going to put in 280. And then the last thing it's going to ask for is the confidence level. And again, this one said a 90% confidence level, so we'll put 0.90 in. And once you put those into the 1 proportion z interval, it'll go ahead and do the whole confidence interval for you. So what will pop out is 0.18395 and 0.26605. And so to match that with these ones, because they're only to 3 decimal places, we're going to want answer choice B. Okay, number 19. Construct a 99% confidence interval for a population mean. So not like the last one. Population mean is when we do the t interval. Assume the population has a normal distribution. A group of 19 randomly selected students has a mean age of 22.4 years with a standard deviation of 3.8 years. So again, because we're assuming that it's a normal distribution, it's okay that our sample size is small. We're going to go ahead and use the t interval because it didn't ask us for error or anything, so we can do the fast method. So the first number that they want is the sample mean. The sample mean is 22.4. The second number that they want is the sample standard deviation. That's the 3.8. The third number that they want is the sample size. They told us 19. And the last number that we're supposed to enter is the confidence level. And this one wanted a 99%, so we enter 0.99. And it'll take care of the rest of the work for us. So 19.891 and 24.909. And so for these ones, we only want 1 decimal place here. So 19.9 to 24.9. That'll be answer choice A. All right. Number 20 actually gives us a list of data instead of giving us the data that we could just plug right in. So we have a little bit extra work to do with our calculator on this one. The grade point averages for 10 randomly selected high school students are listed below. Assume the grade point averages are normally distributed. So we need to go ahead and hit the stat button and then put this into our list. So we'd enter the 2, the 3.2, the 1.8, the 2.9, the 0.9, the 4, the 3.3, the 2.9, the 3.6, and the 0.8 into your list. And then you'll hit the stat button again and arrow over to the one variable statistics so that you can figure out what your X bar is. Our X bar is 2.54. We also need the sample standard deviation, so it'll say S sub X in the calculator. This is going to be 1.1098. And they told us we entered 10 values, so I know that my N is equal to 10. I'll just write that down because we'll need that. We also need the confidence level. And so our confidence level for this one, they told us a 98%. So we'll put 0.98. But once we have all those values, we can just do the T interval because, again, they're not asking us for an error or anything like that. So T interval. And the first thing we'll put in is the X bar, the 2.54. Then we'll put in the sample standard deviation, the 1.1098. Then they want the N value and the confidence level. And again, it's going to do all the work for us as long as we enter that correctly. And so we get 1.5498 as the lower value and 3.5302 as the upper value, which is going to be answer choice A. Right. Next one, a survey of 2,450 golfers showed that 281 of them are left-handed. Construct a 98% confidence interval for the proportion of golfers that are left-handed. So again, not asking us for an error so we can do the cheater method, but it's not going to be the T interval because this one is a proportion problem. So we're going to go and use the 1 proportion Z interval test again. If it, again, is confusing on what's the X and what's the N, sometimes it's helpful to write down the P hat formula. The P hat is X divided by N. So the N value is going to be the total number of people that were surveyed. So that'll be the 2,450, which means that then the X value is going to be the 281. So for the 1 proportion Z interval, it's going to ask you for the X value. So you're going to put 281 first. It'll ask you for the N value. You'll put 2,450. And then it's going to ask you for the confidence level 0.98. And so it's going to give us the full interval for us, 0.09972 and 0.12967. And when you go and look up here, because this one, if we round it to 3 decimal places, is going to make this 7 is going to round this one up, then that's going to make the whole thing get rounded up. So that's going to be 0.100. And this one will become 0.130. So we're going to use answer choice C. A little bit of tricky rounding there. All right, on to the last page. A researcher at a major hospital wishes to estimate the proportion of the adult population of the United States that has high blood pressure. How large of a sample, it's a sample size problem, is needed in order to be 99% confident that the sample proportion will not differ from the true proportion by more than 4%. So we had 2 different sample size formulas to use. The one that this one is asking for is the sample size for a proportion. So that formula was N is equal to our Z alpha over 2 number squared. Then we multiply the P hat times the Q hat. and we divide this by the error bound for the proportion squared. So we need the z critical number, we need the p hat, the q hat, and we need the error. In this particular problem, they don't tell us a p hat or a q hat. And when that happens, we always enter both of those as 0.5. So this one's going to be 0.5, and this one's also going to be 0.5. The z alpha over 2 comes from what confidence level they're asking for. Since it's a 99% confidence level, the z value we're going to use is 2.576. And this would be probably one of the numbers that you would have written in your notes page. You could also calculate it in the calculator. But this one I had people write down the 4 important z critical numbers, and 99% was one of them. The p hat, I said we're going to put 0.5, and the q hat, we're also going to enter 0.5 because they didn't give us those values in the problem, so we always use 0.5 for them if they're not given. And then the error. It says we do not want it to differ by more than 4%, so our error is 0.04, and we're going to put that in parentheses and square it. So we're going to enter this into our calculator carefully. What will pop out is 1,036 and some change. We said when we're doing the sample size problems, we want to round up to the next whole person. So we're going to use 1,037 for this one. This is answer choice C. Number 23, a researcher wishes to estimate the number of households with 2 cars. How large of a sample is needed? Ooh, it's another sample size problem. In order to be 95% confident that the sample proportion, so we're going to use the same formula that we did last time, will not differ from the true proportion by more than 4%. A previous study indicates that the proportion of households with 2 cars is 24%. So they actually just gave us the p hat in this problem. They said the p hat is 0.24. So we can go figure out the q hat by doing 1 minus 0.24. And so 1 minus 0.24 will be 0.76. So for this one, we got a p hat and a q hat, so we don't use the 0.5 like we did in the last problem. In terms of the rest of this, the 95% confidence level is telling us the z alpha over 2 number that we need. So we need the z alpha over 2 for a 95% confidence level. That's our 1.96. And the error, again, is going to be the 4%. So we'll write the error bound for the proportion is, again, 0.04. So we have all the numbers that we need to plug into that formula. Our n is going to equal 1.96 squared. We'll enter the 0.24 for the p hat, the 0.76 for the q hat, and finally 0.04, but we'll square it to match up with the formula. If I plug that carefully into my calculator, I get 437 and some change, which again, we're going to round up to the next whole person. So 438 is what we're looking for, which is answer choice D. Okay. So that was the last of our multiple choice questions, and our very last questions answering a short answer question. In a survey of 10 golfers, 2 were found to be left-handed. Is it permissible to construct the 90% confidence interval for the true population proportion? Explain your answer. Okay, so some people talked about how we just don't have a big enough sample size here. And that's true, but that's not enough information for you to get full credit on this particular one. It's not a big enough sample size, but in particular, what we have to look for, because this is a proportion problem, we had a requirement that n times p hat and n times q hat both have to be bigger than 5. And so lots of people said, well, the n is only 10 and it's too small. That wasn't exactly what we were looking for. What we need is the p hat and the q hat, and we need to multiply those by the 10. So our n is equal to 10. And our p hat then, if we're talking about left-handers in this case, that's going to be your x value over the n. So your p hat is 0.2. And your q hat then would be 1 minus 0.2, which would be 0.8. So we're ready to do the n times the p hat. That's going to be 10 times 0.2. 10 times 0.2 just moves the decimal point over one place. That just pops out a 2. That's not bigger than 5. Now, if I do the n times the q hat, the 10 times 0.8, that actually pops out an 8, and that is bigger than 5. But they both have to be bigger than 5 in order for us to be able to move forward with this. And so they're not both bigger than 5. So because of this one, we are not able to construct the 90% confidence interval. And that's what we were looking for that last one.